everyone, and thanks for joining me. Are you having multiple stages in your manufacturing that require the same features to be inspected? And the current method you use does not allow for those same features to be inspected at different times? Or maybe you just don't have a method. Well, hey, my name is Stefan, Application Engineer at Capture 3D. And boy, do I have a solution for you. Today, I'm going to be showing you how to analyze trends in the ATOS Professional software. Some of you might be wondering, what is trend analysis and why do I need it? I'm going to be answering that today, so be sure to stick around. If you're new here, don't forget to click and subscribe by hitting the button below for other 3D technology tips and features delivered to you by our Capture 3D team. So let's cover some of the background involved with trend analysis. One example I've personally seen in the past are from a mold iteration for a manufacturing company. They had just started a new product line and had developed a brand new mold for their part. Through the iterative process of making a part, scanning it, and then inspecting the trends, they were able to adjust the mold to ensure a perfect part was attained. Simply, an operator can pull a part from the manufacturing floor, let's say one every 10 or so runs from that machine, and this process is what we would call batch sampling. So how can this help us learn more about the manufacturing process? Well, after we take 5 individual batch samples and scan each of those parts with our ATOS scanners, we will then be able to have the measurement data for those 5 individual parts, or what we would commonly refer to in the software as stages. Alright, now let's switch over to the software window and get started. First thing that we're going to do is open up the ATOS Professional software. And what you should see is a window just like this. What we will then do next is retrieve the CAD file by clicking on the CAD and dragging and dropping it directly into our workspace window. Once releasing the click button, we have 3 options. Our first option here is what we will utilize by introducing our CAD file as a new part. Once clicking New Parts, you will see the CAD model pop up into the software. By hitting OK and accepting the default settings, we will then have our CAD file inside the project. What we will then do is go to retrieve our scan file. By going back to our set of data and taking the first scan and dragging and dropping very similarly like the CAD model directly into the workspace window. However, the only difference here is that we will introduce this scan by adding it to the already existing part container. This is important because we want to make sure that our mesh or scan is relative to the CAD. You can ensure this by going and checking your part container and making sure that your CAD and your mesh are all relative to the same parts. This is important because now we would like to go forward with our alignment phase. What you will notice is that the CAD model and the scan data are not aligned in space. And so what we need to do is go up to Operations, Alignment, Initial Alignment, and there you will find Pre-alignment. By establishing a pre-alignment, what will happen is the scan data will then be pulled to the CAD utilizing the overall best fit. By hitting OK, we will have accepted those changes. Now we are ready to move forward with inspecting this part. It is important that when inspecting a part or creating any primitive elements, for example cylinders, like we will be doing in this example, it's important that you have your CAD model exclusive. What I mean by that is going up and clicking on the CAD file and dragging and dropping it directly out into the workspace, and there you will see Show Element Exclusively. By releasing the click button, you will then see the CAD model be the only thing visible within the software. This is important because now once we are ready to go and create our cylinders by going into Construct Cylinder, Auto Cylinder, we want to ensure that we're creating our cylinders on the nominal file, in this case on the CAD. So by holding Control and clicking anywhere on this curved surface, we will have created a cylinder. Let's do this with both cylinders. And after creating these two cylinders, what we then need to do is utilize what we call measuring principles. In our software, we use these measuring principles to tell this how do we want to measure this specific feature. And in this case, what we need to do is access our measuring principles by finding it here in the iInspect wheel, which brings out this same wheel. An alternative way of bringing out that iInspect wheel is by holding the Control button and right-clicking anywhere on the workspace window. This will also bring out your iInspect wheel. And what you will find in the iInspect wheel, up top, using the symbol T, are measuring principles. In this situation, we are going to use fitting element for the two cylinders. In this case, we will accept the default settings of Gaussian best fit with 3 sigma. And by hitting OK, we now have established our actual cylinders based on these nominal cylinders through the measurement principle of fitting element. Once given a measurement principle, what we can then do is go ahead and measure, for example, the diameter. By going into our checks and measuring the diameter of this hole, or this cylinder, we can adjust our tolerances accordingly and accept the changes by hitting OK. And so what you will see is a check. The nominal value expressing the diameter of the CAD file, the actual value expressing the value of the scan data, and the deviation is the subtraction between the two values. So how do we take this a step further? What we will then do is import the remaining meshes. By going into the files, we will take the remainder of the scan files by highlighting them and dragging and dropping them directly into the workspace window. Except this time, we're not going to be adding them to the part. We will be introducing these as a new stage. Once imported into the software, what you will then notice is at the bottom, you will see what we call the timeline. The first thing we need to do is hit recalculate all elements in all stages within our timeline. By clicking that recalculate, it will then measure the same dimension across the stages. And so using that pre-alignment, it will establish the same alignment for all 5 stages in this case. So by alternating here between our stages, you can visualize the results between stages by clicking and alternating between our stages. Now, a better way to do this now is to change the visualization of these checks to utilize our trend analysis features. By holding Control and highlighting this green box around our dimensions, we could then go back into our iInspect wheel and going into the visualization of trend. By clicking on trend, we will then have the option to visualize these diameters across the 5 stages graphically through what we see here in this table. Some additional elements to be observed here are statistical process controls like PP and PPK. Other bits of information like the nominal values, the average, the sigma, and the min and the max. The same table can be viewed in the table format by going up into table and switching from overview to statistical trend. And so now, with all of the dimensions relative to the project, you could then visualize these trends throughout these 5 stages and how this diameter, for example, changes throughout the 5 scans. So, Other ways of viewing this information is through our sources of surface comparisons. By utilizing those color maps, what we can also do is visualize the color maps in such a way that it will take into calculation all 5 scans, or all 5 stages in this case. By assigning some arbitrary tolerance of 0.01 inches and hitting OK, we will then have created a surface comparison that will then be repeated throughout the 5 stages. Once the software has calculated these 5 surface comparisons, what we can then go ahead and do is change our legend. By linking the two to form a unilateral tolerance, we will then be able to give the option of an adjusted legend tolerance. I will choose some arbitrary number of 0.01 inches, for example. And so by changing that, you will then be able to see in color how this specific stage, in this case example stage 6 or 5, and how it compares to the nominal set of data. By alternating between the stages, I can visualize those color maps and how they compare to the CAD. So, utilizing our trend features now, we can go up top and create a deviation label. To be able to create these labels anywhere you'd like to place by holding Control and clicking anywhere on the color of the surface comparison, we could then highlight those deviation labels, and very similar to our dimension previous, we can also visualize these dimensions as a trend so that we can track how those specific points are changing throughout the 5 stages. So now what we can do is take this a step further by visualizing the surface comparison exclusively by going into Inspection, Surface Comparisons, and taking our surface comparison out by itself to show it exclusively. We then have the option to change between our label or legend templates. And so what you will see here is that not only do we have the option between legend and tolerance legend, which comes standard to projects without stages, you will then have things like minimum and maximum, arithmetic mean and range. These color maps can also be visualized, which are taking into consideration all 5 stages at the same time. So as I alternate between the timeline, you will notice that the color maps do not change. Just like we can change to range, other important graphs that can be pulled from this are, for example, the CP value graphs. Statistical process controls that can help an engineer figure out where the part is having the most problems. Utilizing these color maps, we could then observe all 5 stages within the same color map. Okay, so we just went over how to analyze trends in the ATOS Professional Inspection software. We first started by importing our CAD model and following that the 3D scan data of our actual parts. Once we had both of these in the software, we were then able to measure the changes between those individual stages and how the features changed, for example, the diameter of the cylindrical surface. Some other interesting applications of this process could include tracking a part over the change in time versus temperature. For example, you can scan the same part throughout a typical day to compare how that scan data is affected by the varying temperatures throughout a given day. Alright, well I hope you enjoyed this video, and now that you have the knowledge, please try this out on your own. Don't forget to please click and subscribe by hitting the button below, and make sure that you're notified of new content and tutorials from our Capture 3D team. Also, please visit our website for any case studies, or if you'd like to schedule a one-on-one with our team. Thank you for watching, and have a good day.